Okay, so this video will be an introduction to continuous random variables. For a motivation for a continuous random variable, we are going to discuss something called the uniform distribution. We will come back to it again in another later video where we will calculate expected value and so on, and things like that. But for now, we're just going to use it to motivate the concept of a continuous random variable. Okay, so continuous random variables then. So just like discrete random variables, again a continuous random variable is the name given to a function mapping an abstract probability space. So this is our abstract probability space, which is a sample space, a set of events, and a probability measure. And the continuous random variable, which we will still call x, capital X, is going to be this mapping from this abstract space to some standard space with outcomes in the real numbers. So to each outcome in this abstract space, it's going to ascribe a real number in this standard real number space. And basically, in contrast to the discrete case, where we had either a finite, the image of this function basically, all the elements that are in this set, you either had finitely many of them, so in the discrete case you had finitely many real numbers in here, or you had count of the infinite. Which means that the number you had could be listed. It could be placed in correspondence with the natural numbers, which are 1, 2, 3, 4, 5, and so on. Whereas in the continuous case, it's more analogous to the continuum. And later in this video, I will explore this, because this does not mean at all that, for instance, the CDF of continuous random variables is in fact continuous. No, it means that that this space of numbers here is potentially uncount of the infinite, i.e. you can put it in bijection with the real numbers, i.e. you can put it in bijection with the continuum, in bijection with continuum. Okay, and that's all that means. All that is a set theoretic bijection. I'm not saying that it's going to be isomorphic in any other way than in the set theoretic way of in the set theoretic sense. So they're not potentially going to be topologically homeomorphic to the real numbers continuum, but it's as far as just making a bijection is concerned, you can do that. So it's in bijection with the continuum, which is why it's called a continuous random variable. It has nothing to do with the concept of continuity in real analysis. Okay, let's look at a basic example of a continuous random variable to see how this works. So let's take the probability space. That is, let us take a small interval, or a small geometric interval like this, and the question is, the game is that I am going to randomly choose a point in this interval. So you can choose whichever point you want in this interval, and basically we want the space of all possible outcomes. So I'm going to make this space of all possible outcomes. So for instance, I could pick this point over here, I could pick any point in here. So in fact, I'm going to have an image of the entire interval in here, which is every possible point in here is going to be a possible outcome of my choosing a single point on this interval. Okay, so now we could set up a continuous random variable, which is going to be like this. So you're going to map the outcomes here onto the real line. So let's map this point, let's call this point 0, and let's call this point 1, and we're going to map it so that effectively it is a topological homeomorphism. So all we're going to do is basically either shrink it down, probably shrink it down in this case, we're going to shrink it down so that all the bits in between go to 0 or 1. So we're going to send this point that's exactly halfway between. In fact, it's going to be more than just a topological homeomorphism, because of course if it was just topologically homeomorphic, I could take this point over here to a half and squash up this bit. No, I want it to preserve its geometric properties. All I want to do is basically shrink it down onto 0, 1. So I want to make this point 1 and make this point 0, and I want to give any point in between. So if you take any point here in between, I want to give the number between 0 and 1, which is the ratio of this one to this one. So basically, how I want the number that it goes to over here to have the same ratio, to be the ratio of this one divided by this one in effect. So if you take the length of that and divide it by the length of the whole interval, I want that to be the number it's taken to over here. So that's a continuous random variable because you are mapping it onto the interval 0, 1, which is an uncountably infinite set and indeed can be put in bijection with the whole continuum. Okay, so there's an example of a continuous random variable. Okay, so now what we're going to do is we're going to look at the concept of a CDF for a continuous random variable. Now you see the problem with continuous random variables is that we no longer have the concept of a probability mass function. Probability mass functions. And you see the problem is that in the discrete case, we had the option of putting every single outcome into a set by itself, calling that an event and ascribing a probability to it. We don't have that outcome here, that possibility here, because if you do, well, you can do that. You certainly can do that. You can put every single outcome, so I can have the set containing 0, but the probability of that is equal to 0, and in fact the probability of any single outcome put in a set by itself and taking the probability of that is actually 0, because if you think there's an uncountably infinite number of possibilities here, the actual probability that you're going to get a single spot on that interval is actually 0. It's infinitesimal, if you like, but you can't ascribe a non-zero probability to that. And you might wonder, well, why can't we argue in the same? How is this possible? Because surely the whole interval, if you take the whole space, let's call this standard probability space over here. We'll call that omega prime, f, and p prime. So that we'll make them all the primes. Then if we take the probability p prime, this should be here, p prime of the entire space, well, we could say the whole space is the union of every possible single outcome. P prime of the union over x is an element of 0, 1 of the singleton containing x. Now, that is a disjoint union. The problem is it is not countably infinite. So previously what we said is we'll apply axiom 2 of probability spaces and say that this is equal to the sum, x is an element of 0, 1, p prime of the singleton set containing the single outcome x. The problem with that is that axiom 2 does not say that you can do that. It does not say that this is equal to this. And obviously it doesn't say that, because otherwise you'd be summing up zeros, and obviously that would be it wouldn't satisfy the axioms. It wouldn't satisfy axiom 1 of the probability space, that this has to be equal to 1. And the reason that does not break axiom 2 of probability spaces is that this is an uncountable union, and axiom 2 of probability spaces just said that this needed to be true for countable unions. Okay, so you cannot, the probability mass function is not a terribly useful concept. You can define it, it's 0 for absolutely every single outcome. Obviously, we'll come back to it in certain places, because for silly distributions like the Dirac delta distribution, things change and the probability mass function goes a bit odd there. But for general continuous random variables, for this problem here, the probability mass function is going to be equal to 0 everywhere. So it's not terribly useful, because it does not completely characterize our probability distribution at all. Giving me the PMF, telling me that the PMF is 0 everywhere, does not help me, does not uniquely specify this distribution anymore. So we want another way of specifying the distribution, don't we? So there is a way of doing that, which is the CDF. The CDF was a way that we had for discrete random variables. We used the CDF to completely specify discrete random variables, and we said that the probability that the random variable is less than or equal to some little x is going to be given the symbol big F of x, which is the CDF So this is going to tell us, you give me a value of the random variable, I will tell you what the probability of the events that you are less than or equal to that actually happening is. Okay, and that completely specifies the distribution for a countable, for a discrete random variable, because given it, you can get back to the PMF and you can go between them, and the PMF completely specifies the distribution in the case of a discrete random variable. If you can get the PMF, then you obviously know what your distribution is. But this still works in the continuous case. So for instance, let's see that here. If we want the probability that x is less than or equal to x, then if you take any x on this interval 0 to 1 here and ask what is the probability that it is less than or equal to x, because I threw this completely randomly, that must be proportional to that must be equal to x, and also because this is going to 0 to 1, between 0 and 1. So it's equally likely to it's equally that to see this easily, let's consider if we went to the point a half. Let's say if x was equal to a half, then you're equally likely to go in this portion as you are to go in this portion here, because the throwing is completely random. So if we make this smaller, then obviously you're less likely to go in this bit than you are to go in this bit, because this bit's bigger. But the measure of how likely you are is going to be equal to x, because x is the ratio between that point and 1, because all you're doing is dividing through by 1. So I hope that's clear, that the probability that this random variable is less than or equal to x is equal to x. And that is the CDF for this distribution. And that completely specifies this distribution, because it tells us the probability of enough events that if you were given any other... So let's say you were given... Okay, I want to show you basically that if you're given any event, you can, from the CDF, you can work out what the probability of that event is. So remember the definition of a probability distribution. The probability distribution on a standard probability space like this, where we've got elements in the real numbers, is just another name for this probability measure. So it's this function ascribing a value between 0 and 1 to every set that is in this set of events. Okay, so in this continuous case, then events take the form of sets that are intervals, or countable unions of intervals. For instance, if you have something along the lines of you want the event that x is between, let's say, some a and some b. So if we have our interval 0 to 1, then we might have some a here and some b here, and we want the probability that it's in there. So that is an event, this interval ab. Oh, and note that in continuous random variables, it does not matter, obviously, whether this is the closed interval AB, or whether it's the open interval AB, or whether it's half open, half closed. The probability of these events is exactly the same, even though these events aren't the same, because they differ by the points AB, but the points AB have probability 0 anyway, so that doesn't actually affect the probability. So if we have an event of this form, which is an interval, and we want to know what is the probability of an event like this, then what we can do is we can take the probability that x is less than or equal to b and subtract off the probability that x is less than or equal to a, and that will give us the probability that x is between a and b. So from the CDF, basically, we can access the CDF, the probability of any event here, and any event that's going to have a non-zero one is going to have the, it's going to be more complicated than that, but basically, your set of events needs to, without doing measure theory, this is quite difficult, but the set of events has to obey some properties. You want it still to obey the fact that this measure is going to be countably additive, and to make that hold, this now has a lot more restrictions on it than it did in the case of discrete random variables. So in the case of discrete random variables, remember, when we had these standard probability spaces in the real line, and they were just either finitely many many real numbers in those spaces, or countably infinitely many, you know, we could just let the set of events be the power set of that set of the sample space. We could define the probability for any event, and that was very, very nice. And we could, as long as we knew the PMF, i.e. the probability of each singleton in a set, then we could define. We could just define the probability of any other set to be the probability. We could express any other event as the union of those singletons, and then split up the probability of that event into the probability of the single outcomes that it's made up of, and add all of those together. And then you're pretty much assured that the probability measure is going to obey countable additivity. Here you are not. You cannot do that. You cannot define. In a lot of cases, you will not be able to define a probability measure on the power set of the set of outcomes, and that's a very, very difficult question of how exactly we create these sets of events. So for simplicity, you can just think of taking the set of events in this probability space, for instance, this 0 to 1 interval. Let the set of events be the intervals and all countable unions of intervals, i.e. If you had something like this, so this is 0 to 1, so here's an interval, you can union another interval up, you can union another interval up, and you can union countably many together, and you'll still get an event. So basically we're going to define it almost to be the similar to the open sets, but you can have intervals that aren't open, so for instance AB. So it's all intervals, so whether they're closed, open, or half open, half closed, and then all countable unions that you can get out of unioning just intervals together. Then you're pretty safe. You're pretty safe that you can define a good probability measure on it, because all you'll do is basically either when you union the intervals up, they won't overlap, and then what you'll just do is define the probability of it to be the sum of all the probabilities of the individual intervals, or if they do overlap, just union them together, you'll get another interval and take the probability of that, basically. Okay, so that can get very complicated, and measure theory is the foundations of how to deal with that. So what else do I want to discuss in the concept in this video? Okay, yes, so I want to discuss the concept of a PDF now, so probability density function. Probability density function. Okay, so just to finalise the stuff on CDFs that we did, so we had our random variable, we had this abstract probability space, which consisted of the sample space, the set of events, and a probability measure. We then had a random variable x, which was mapping it onto the interval 0, 1, and just for future reference, you could say that x is distributed uniformly onto the interval 0, 1, like that. That's the standard name for this standard distribution here, which is the uniform distribution, where you're equally likely in a way, if there was such a thing as a PMF, which we're going to create an analogous thing here, which is the probability density function. If there was an analogous thing, they'd all be equally likely. If you could ascribe a probability to each of these singleton points, they'd all be equally likely. Okay, and we found that the CDF of this random variable, f as a function of little x, that should be, we could, if you want, you can put a big X down here to show that it's the CDF of the random variable big X. Okay, and we've found that that was equal to x, basically. So if we plotted this, it's x if x is an element of 0, 1. But remember, the CDF is actually defined on the entire real line. So it's 0 if x is less than 0, and it's 1 if x is greater than 1, because it's asking, remember, what is the probability that big X is less than or equal to x. So you can define that for any real number. If the real number is less than 0, then obviously the probability is going to be 0, because there are no possibilities that are less than 0. Okay, so if we were to plot this CDF, then it would look something like this. You'd go along 0, 0, 0, and then you'd suddenly get to 0, and it will remain at 0 because 0, if you put 0 into here, you still get 0, and then it goes up, 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 up to 1, let's say this is 1, at 1, and then it basically stays at 1 forevermore. So that's a nice simple CDF. Now, the concept of the probability density function is the probability density function, PDF for short, which is denoted little f, is going to be defined to be the derivative of the CDF. So if you can differentiate the CDF, and that is not given, it's if big F of x is differentiable. And if it's differentiable, it's a theorem from real analysis that differentiability implies continuity. Now, saying that x was a continuous random variable does not mean that the CDF is continuous. I want to stress that. It means that this set is placeable in bijection with the continuum. It does not mean that the CDF is continuous. So it might not be possible to define f prime, it might not be possible to define a PDF, but if you can, and for all the nice ones, all the famous ones, you usually can. So for instance, the normal distribution, the most important distribution of all the statistics, you can define this, and for this uniform one you certainly can define it because you can take the derivative everywhere along here. It's certainly continuous. Oh well, actually I stand corrected. You can't take the derivative there and you can't take the derivative there. So even on this simple example, there are points where the derivative does not exist. So that's a little bit unfortunate. But nearly everywhere you can differentiate this function, and obviously here the derivative is constant. So that fits with our idea that if this is a uniform distribution, this analogous concept to probability mass function should be equal everywhere. Well, if we define this probability density function is going to equal, it's going to equal 1 on if x is an element of 0, 1. The open interval 0, 1 now, because at 0 and 1 we have some problems there about what the derivative is. So that fits with our concept of the fact that the probability mass function, the analogous concept for the continuous random variables of the probability mass function, should in some sense be uniform for this uniform distribution. Okay, so why is this a good concept? Why is this a good concept? Okay, so what does the derivative mean? Let's examine what the derivative means. It means the limit as h approaches 0 of f of x plus h minus f of x divided by h. So basically it says go forward, or go back. In fact, you can h, there's nothing here that says h has to be greater than 0. H just is not equal to 0. Okay, but often we do think of going forward when we differentiate. So go forward a tiny little amount h, and you go up a certain amount. So you go to f of x plus h. So if this is this distance here is h, so it was x, then it goes to x plus h, and you go up a certain amount. So here is f of x, and you've gone up a certain amount, f of x plus h. And of course, CDFs are always monotonically increasing. They can stay the same, obviously, for whiles, but they are always monotonically increasing. So f of x plus h is always going to be bigger than f of then that should be a big f of x. Okay, so you can ask how much bigger this is going to get. That's how much. That's this difference here, and then what you're doing is dividing it by h. So in a way, what it's saying is, as you let this get infinitesimally small, you're saying how likely is it going? Because okay, let me start again. F of x, big F of x plus h minus f of x is equal to the probability that you pick a point in the interval x to x plus h, isn't it? In fact, it's the closed interval x to x plus h. So it's the probability that you pick that when you pick a point in in this interval 0 to 1 that you're within that tiny little interval h, and as you make h smaller and smaller and smaller and smaller, obviously this probability is going to get smaller and smaller and smaller, and that's what we mean by saying that the probability mass function is going to be equal to 0. But of course we can divide it, we can scale it by h. So if we divide through by h, we no longer have the probability that you pick a point in h, but we have the ratio between the size of the interval and the probability that you'll be in that interval, and that's the concept of the probability mass function. So if you multiply f of x by some tiny little h, then that's the probability that it will be. It's roughly equal to the probability that it will be in that little interval. If you want the exact probability, of course, it's really big F of x plus h minus big F of x. But that is approximately, so this is approximately equal to big F of x plus h minus big F. So it's approximately equal to this, this value here is exactly equal to the probability that you'll be in a point, but this is approximately equal to this. So this here is approximately equal to the probability that you'll be within a tiny little interval of size h. So that's what the motivation for defining the concept of a probability density function comes from. So think of it as kind of the best, making the best of a bad situation. We are doing the best we can where we can't no longer have the concept of a probability mass function, so instead we have the concept of a probability density function. Okay, and of course this also, so the probability density function also uniquely specifies the distribution, specifies the probability distribution, Okay, and also if we know, because we can go backwards and forwards, so how, if we know the probability distribution density function, can we go back to the probability, the CDF? Well, basically we can integrate if we know that little f of x is equal to f prime of x, then if we integrate both sides, if we integrate little f dx, the problem here, the slightly difficult thing is what do we integrate it between? Well, we integrate it between negative infinity and x, and I hope that's obvious from what I've said here. The probability density function you can think of, if you multiply it by this tiny little interval h, that's giving you the probability that it's going to be in that tiny little interval. So if we add up all of those from negative infinity to x, we're going to get the probability that it's less than or equal to x. So this gives us back the CDF, big F of x. Okay, and similarly, if we want the probability of some event, so let's say if we want the probability of some interval AB, and I should really put P prime there, if we want the probability of some interval AB, we've agreed that that is big F of B minus big F of A, but that looks very much so like the fundamental theorem of calculus, doesn't it? So big F of B we could define as being, from this formula here, is equal to the integral from negative infinity to B of f of x dx minus the integral from negative infinity to A of little f dx, and then we can just, from the fact that we know that A is less than B, we can combine these two together to say that this is the integral from A to B of a little f of x dx. So in a way, you can the pictorial representation of this is we've got some probability density function all the way along, like this, let's say, and if we want the integral all the way up to b, then that's the area of all of this, and of course it will converge, so this picture's probably a bit off. And if we want the integral up to a, which is this bit here, we want the area all the way up to there. So if we subtract them off, what we're going to end up with is just this area that's left between them here, which is the probability that it's going to be between a and b. Okay, so that's how you get the probability of an individual function like this. Now, because, and that's the fancy mathematical symbol for because big F of x, the CDF, is monotonically increasing, that implies that the derivative f prime of x is always greater than or equal to 0. So if we look here, because it's always either getting bigger than 0 or staying at an equal value, the derivative can never be negative. Otherwise, the point infinitesimally further forward than that point is going to be less than it. So then it wouldn't be monotonically increasing. Okay, so f prime of x is always greater than or equal to 0, which implies that the probability density function is always greater than or equal to 0, since it was defined to be this. Okay, so probability density functions are always greater than or equal to 0, and also we know that the integral from negative infinity to infinity, which of f of x dx, which by this formula here would be equal to well, it would be equal to the limit. I shouldn't just write big F of, I can't bring myself to write big F of infinity. So I should say the limit of big F as n approaches infinity. And we know, of course, from properties of CDFs that that is going to be equal to 1. So the integral of our PDF between negative infinity and infinity should also be equal to 1. So there are some basic properties of PDFs. And there's one little thing that I should add, which is that in the case of PDFs, you can't guarantee that there is no guarantee that the PDF, the f of x, is less than or equal to 1. It could be greater than 1. That is not true, basically. And let me show you why. If I take an analogous CDF to this, but I make this line steeper up like this, then the PDF is the gradient of this line. Now the gradient of this line was equal to 1, so if I've made it steeper up here, this is still a valid CDF, a perfectly valid CDF, and I could work out what the PDF for it is. Remember the properties of CDF, monotonically increasing, right continuous, which it certainly is, and that the limits as you go off to plus infinity are 1, and the limit as you go off to negative infinity is 0. So this certainly satisfies the properties of CDFs that we know and love. But the gradient of this was equal to 1, so the gradient of that is going to be bigger than 1, so the PDF at this point is going to be bigger than 1. So there's no guarantee that the PDF is going to be less than or equal to 1. Okay, and now what we're going to do, that final thing we're going to do in this video is we're going to generalize the concept of expected value to continuous random variables, expected value. So recall that the expected value for a continuous random variable, e of x, for a discrete random variable, was equal to the sum over every possible value x could take of x times the probability that big X was equal to little x. Right, so it becomes more difficult now, much more difficult, because firstly, we do not have a PMF anymore. We do not have, this does not exist anymore, it's just equal to 0. So we wouldn't get a very interesting sum if we just did this for every value of x. The other thing is we're summing over an uncountably infinite number of possible x values. So, we know that the probability that x is equal to a specific value, the best way we can approximate that is by saying it's equal to the PDF, which is little f, times an absolutely tiny little h. If we make h smaller and smaller and smaller and smaller and smaller and smaller and smaller, it's getting more and more it's getting closer and closer to the probability that it actually is equal to that point. So, if I let this converge on being infinitesimal, imagine it's infinitesimal, and this of course isn't rigorous maths, but if we imagine it's getting infinitesimal, this is the motivation for how you get this formula, that this kind of replaces this differential value for this probability. Okay, and then what we're doing is we're summing over this, we're summing infinitesimals over a countably infinite number of things. So effectively what we're doing is integrating. We want to take each value of x, we want to multiply it by the probability that it's in there, and then we want to sum that over every possible value of x, which is x can vary between negative infinity and infinity. So that is the way we will define expected value for a continuous random variable, and I hope what I've shown you there is that it is reasonably analogous to this sum. We've replaced this probability, which was finite here, by a differential probability. We've multiplied it by its x values, and now instead of summing, because we cannot sum up differential quantities. Instead of summing, we are integrating, which is the analogous concept of summing over differential quantities, and then sort of out of this uncountably infinite sum of infinitesimal things, we somehow arrive at a finite value, which is what's incredible.